Hello and welcome back to your Chem 4 lecture. Today we're going to wrap up chapter 14 by talking about amines and amides. So what these compounds have in together is, what they have in common, is that they contain nitrogen. So that's what we're going to be focusing on today, is the combination of nitrogen in organic chemicals. One example here is indigo. Indigo is an amine containing compound, similar to what we'll be talking about. Okay, so amines are derivatives of ammonia. Ammonia, you may know because I've been talking about it a lot this semester. It's an extremely important chemical, basically as a basis for a lot of other things. It doesn't show up in our biology because it's very toxic, but it is very reactive, and we can understand our chemistry a lot better if we understand the chemistry of ammonia. Now, ammonia is NH3, so that's a nitrogen bonded to 3 hydrogens. It's commonly used as like a cleaning agent, for example. A lot of window glass cleaners have ammonia and has a very sharp, pungent odor that you recognize immediately if you've ever had to do a lot of cleaning for whatever, home or job or whatever you have to do it for. And what it is basically is you take an N that's connected to one or more alkyl or aromatic groups. Note, nitrogen, when it's attached to a carbonyl, is no longer an amine. That's an amide that we're going to be talking about later on. So it's only when it's bonded to an alkyl or an aromatic group. So these are all examples of amines here. Now, amines have a very important classification system, similar to alcohols, but notably different. So remember, we classified alcohols as primary, secondary, or tertiary, depending on the number of carbons that the carbon bonded to the hydroxyl group was bonded to. Now we're going to do something similar for nitrogens and for amines, but notably, when we're talking about primary, secondary, and tertiary amines, we're talking about how many carbons are actually bonded to the nitrogen atom. So for a primary amine, that's where the nitrogen is bonded to 1 carbon chain and 2 hydrogens. For a secondary amine, that's where it's bonded to 2 carbons and 1 hydrogen. And then for a tertiary amine, or 3 degrees, that's where it's bonded to 3 carbon groups and no hydrogens. So this is another way to view it if you're thinking of the molecular models. Ammonia, of course, would be a 0 degree or 0 order amine, but there's only the one, so we don't give it a special name. Here we have the primary amine, like methylamine. Methylamine is where you have a methyl group coming off of the nitrogen in the amine. Then you have dimethylamine. That's where there's 2 methyls on the nitrogen. That's a secondary amine. And then finally, for the tertiary amine here, we have trimethylamine, where there's 3 methyl groups all sticking off of the nitrogen. Okay, so we're only going to be worried about the simple nomenclature for amines in this class. So this is not the IUPAC system, but it is a very important system, and it does work really well for a lot of common names for amines that you might be dealing with in the future. So we name them as alkyl amines. What we do basically is list the names of the alkyl groups that are bonded to the nitrogen in alphabetical order in front of the word amine. And the prefixes are going to identify any duplicate alkyl substituents. So like here, for example, we know, okay, we've got a nitrogen, it's bonded to a carbon chain, and it's a 2 carbon chain. So that's an ethyl group. So we would name it as ethylamine. Next up, for the second one here, we've got a nitrogen in the middle, bonded to 2 methyl groups. That's dimethylamine. And then finally, if we had an ethyl group with 2 methyl groups on the same nitrogen, we would call that ethyl dimethylamine. Okay, so go ahead and give it a shot here. Give me the common name, that's the simple name we've been talking about for each of these amines, and classify it as either primary, secondary, or tertiary. Give it a shot, and we'll take a look at the answer when we come back. So pause the video and give it a try. Okay, let's take a look here. So A, we have a nitrogen here, and it's bonded to 1 carbon and 2 hydrogens. That's a primary amine. When we look at that carbon group and we got 1, 2, 3 carbons in a row, that's a propyl group. So we would call this propylamine, and it's a primary amine. Next up, this amine here, we have a nitrogen that's bonded to 3 different carbons, so that's a tertiary amine. And we look at the substituents, we see we have 2 methyl groups and an ethyl group. E comes before M in the alphabet, So we're going to name it ethyl dimethylamine. Okay, now that's for the simple amines that we've been talking about. Now, there is another type of amine that is really important, which is known as aniline. This shows up every so often as substitutes on like various drugs, for example. While itself is pretty toxic and in fact a sterilizing agent for men in particular, in combination with other compounds can be important. So aniline here, we would name it just like anything. So if we have a substituent on the aniline, we know that we have to name the carbon on the ring that's bonded to the nitrogen as carbon 1, and then we number it from there. So for example, here, the bromo is on the carbon 4, so we name it 1, 2, 3, 4. This would be called 4-bromoaniline. However, that's not the only place a substituent can be. It can also be on the nitrogen itself. For example, what if we have a methyl group on the nitrogen? Well, rather than trying to name it some other thing, we're going to say, okay, we know the methyl group is on the nitrogen. So rather than numbering it, we're just going to say N-methyl. So it's aniline with a methyl group on the nitrogen. So it's N-methyl-aniline. So we'll have some practice with this later on. It's also important for amide nomenclature, which we'll talk about in the future. Okay, go ahead and give me the common names for each of these amine compounds. So pause the video, come up with the answers, and we'll take a look when we get back. So pause the video here. Okay, let's take a look here. So up top, we've got a nitrogen. So it's an amine, and then it's bonded to an ethyl group, another ethyl group, and a methyl group. So there's 2 ethyl groups. E comes before M in the alphabet. So diethyl methylamine. Then down here, we have an aniline, right? Because it's a nitrogen bonded to a benzene ring. So we know it's aniline. There's no substituent on the benzene ring, but we have an ethyl group on the nitrogen. So we're going to call that N-ethyl aniline. Okay. All right. So line angle formulas. We probably don't need to spend too much here, but what we do is we make sure that for the line angle formulas, we are going to draw in the hydrogens that are on the nitrogen. Remember, we don't draw in hydrogens when they're on carbon, but when they're bonded to oxygen or nitrogen, we do want to draw them in because oftentimes they're going to be reactive if they're bonded to nitrogen or oxygen. Okay, now let's go ahead and talk about the solubility of this. So primary and secondary amines contain nitrogen-hydrogen bonds, and because of that, they can hydrogen bond with water. So any primary or secondary amine that has fewer than 6 carbons will be soluble in water. And again, that's because you have a lone pair on the nitrogen that can form hydrogen bonds to the hydrogen of a water molecule. And you have these hydrogens that are bonded to nitrogen that can form hydrogen bonds to the oxygen of water. Tertiary amines can only form hydrogen bonds with water molecules, not to each other. And so they tend to be less soluble in water. Oh yeah, I guess I've already said this here, but primary amines have 2 hydrogens, so they have the ability to form hydrogen bonds to 2 separate oxygens. And then tertiary amines can only form hydrogen bonds to a hydrogen. Yep, okay, and smaller amines, even tertiary ones are soluble. So like trimethylamine, for example, is soluble in water because of those hydrogen bonds. Okay. So anytime that you have an amine that has more than 6 carbon atoms, the number of nonpolar bonds is going to basically outweigh the number of hydrogen bonds that the molecule can have. So again, what we're going to say is that anything above 6 carbon atoms is insoluble in water. Anything below 6 carbon atoms for an amine will be soluble in water. So applying that knowledge, let's go ahead and look at sample exercise 11. Tell me which of the following, and it can be more than one, are soluble in water. So tell me insoluble or soluble for A, B, and C. Pause the video, and when you're ready, let's take a look. Okay, well, it's pretty straightforward. A and B both contain amine functional groups, and they have 1, 2, 3 carbons for both of them. 1, 2, 3. 3 is less than 6, so we know that the hydrogen bonding aspect is going to outweigh the nonpolar carbon, hydrogen, and carbon-carbon bonds and lead to them being soluble in water. C, on the other hand, does not have this amine group, so it can't form hydrogen bonds with water, so it will be insoluble in water. Okay, now amines can also act as bases in water. This is a very important part of their reactivity. So ammonia, primary and secondary amines, will act as Bronsted-Lowry bases because they have this lone electron pair in nitrogen that is able to accept a proton from water. So here we have ammonia, NH3, just as a simple example. When it reacts with water, it forms the ammonium ion, NH4+. In other words, it acts as a base to accept a hydrogen ion from water. And that means the water is acting as a base here, or I'm sorry, it's acting as an acid to give its proton to ammonia. And that leads to the ammonium ion, hydroxide ion. Now, it's not just ammonia that can do that. Any amine can do it. So for example, methylamine here, which is just a methyl group on an amine, can also act as a base and form an ammonium ion. Now in this case, because we have a methylamine, a methylamine has, when it's protonated, becomes methylammonium ion. And this is across the board. So for example, if you had triethylamine, when it's protonated, it becomes triethylammonium. So just the amine word becomes the word ammonium. And what was, NH2 in this case becomes NH3+. What you do is basically add one hydrogen atom and a positive charge. Okay, so now amine salts are really useful. And again, it's used in every day. So for example, you may note that fish dishes smell fishy, and that can be an unpleasant odor in some cases. Sometimes it's nice, but if it's overbearing, one thing that you can do to reduce the fishy smell of fish is add an acid, like for example, citric acid from citrus fruits. So when you squeeze a lemon here, you're adding acid to a fish that contains amine compounds. Those amines are volatile, and so you can smell them, and that's what causes the fishy smell in your nose. When you add acid to it, then they form an ammonium salt. And that ammonium salt then is no longer volatile. It has to stay on the fish, so you don't smell it as much. Okay, so for example, you can take methylamine and add HCl, and what happens is you form the methylammonium ion with the chloride left over from hydrochloric acid. That becomes methylammonium chloride. Dimethylamine then would be dimethylammonium, and with the counter ion from the strong acid, that's dimethylammonium chloride. Now, another reason that ammonium salts are really important is that amines tend to be liquids and ammonium salts tend to be solids. Ammonium salts being solids means that they're a lot more useful for drug formulations. It's easy because, first off, they don't smell, as we mentioned. They're soluble in water and in your body, and also they're shelf stable. They're not going to decompose as easily, usually. So let's look at some examples of ammonium salt medications. So we have ephedrine, for example. This is a bronchodilator. So it expands your lungs, I want to say, and the whole air passage. And it's used in Sudafed, which is a decongestant. And then diphenylhydramine or diphenhydramine is found in Benadryl, and that's this here. Again, both of these have amines in them, but they've been protonated to form ammonium salts. So this is ephedrine HCl, and this is diphenylhydramine HCl. Again, both of them, you see the ene here, INE, that tells you that there's an amine involved. And then plus the HCl means that it's the ammonium salt of the amine. How about narcotics? Well, if the medical industry knows about this, then the illicit drug industry knows about it as well. So cocaine is an ammonium salt of cocaine. So cocaine hydrochloride is like the white powdery stuff that you see, on movies and stuff like that. You can extract cocaine from coca leaves using an acidic solution, and that gives the white powder cocaine that you think of. Now, the thing is that cocaine as a white powder is not as strong as it is when it's just a free base. basically this can be more active than the cocaine salt itself. Sorry, it's a little confusing because there's no difference in the name here. It's both cocaine hydrochloride and cocaine, which is the free base, crack cocaine. So what people do is to make crack cocaine, what you do is you have to react the cocaine hydrochloride with a base. Now, don't use sodium hydroxide. Not that you're doing to do this at home, but people don't use sodium hydroxide. They use baking soda, I believe you can use. And that is enough to deprotonate it and form the free base. This is a volatile liquid that can then be inhaled. And that's the crack cocaine that basically like is stronger. It's not like it's stronger. It's the same drug. It's just it's more processable by the body. So you get kind of a higher concentration of in your lungs. Okay, linking that, cocaine is an example of what's called an alkaloid. So alkaloids are any physiologically active compound that's produced by plants and contains nitrogen. And there's just so many of these alkaloids that it's really difficult to state, you know, understate the importance of them. So anesthetics, antidepressants, stimulants, and there's also a lot of degree of habit-forming nature of these drugs. So like we mentioned cocaine before, there's also nicotine, for example. Nicotine here is given here. You can see that there's an amine in nicotine. And nicotine is a stimulant. And what that does is basically increases the amount of adrenaline that you have in your blood and increases your heart rate and blood pressure. So it hits the pleasure centers in the brain, and that allows you to, you know, that's going to get you hooked on it, basically. Real problem with nicotine is that it is involved in tobacco. So like smoking it, smoking anything into your lungs can be really problematic because smoke itself contains all sorts of cancer-causing compounds. And you know, if you're putting those in your lungs are very sensitive, of course, so you're kind of leading yourself to getting cancer in that way. Slightly less illicit, I guess, than that is caffeine. Caffeine is another example of an alkaloid. That's the structure right here. Of course, this is in coffee beans, tea, and chocolate. And this is another central nervous stimulant. And this leads to an increase of alertness, but it may cause us insomnia, and it is definitely habit forming as well. So just keep that in mind. Finally, we have some opioids here. Two examples here are morphine and codeine. There's a whole class of opioids that are all kind of related to one another. So for example, morphine and codeine, the only difference is what is an alcohol group or hydroxyl group in morphine is turned into an ether group in the codeine. So that's kind of the difference between the two. These are used as painkillers, and they're very effective at painkillers, but they are also extremely habit forming. Okay, so let's go ahead. Given all of that, why don't we go ahead and talk about the condensed, give me the line angle formula here for methylpropylamine and 2-chloroaniline. So don't worry about the condensed structural formula. Just give me the line angle formula and for both here, methylpropylamine and 2-chloroaniline. Let's pause the video, and when we come back, we'll take a look at the answers. So pause. Okay, let's take a look here. So methylpropylamine, that's going to be an amine that has a methyl group on one side and a propyl group on the other. And as you can see, it's a secondary amine. 2-chloroaniline, on the other hand, that's aniline, so it's a benzene ring with the NH2. And then the chloro has to be one carbon away from the NH2 here because it's on the 2-chloroaniline. This is carbon 1, this is carbon 2. Okay, so we got through the amine talk. Now let's go ahead and talk about amides. And we talked about aspirin earlier. A related compound is acetaminophen, which is known as Tylenol. So aspirin can have its own side effects. Basically, it thins the blood, and that can lead to some desirable side effects, but then also some negative side effects or consequences. For example, if you're like, if you like cut yourself and your blood isn't clotting in the right way, that can be a real problem. But this is good at least for like headaches, for example. Okay, so let's go ahead and take a look at amides. First off, amides, you can see that they're related to both carboxylic acids and amines. what it is basically is you have a nitrogen group that replaces the OH group of a carboxylic acid. So there's a carbonyl, and that carbonyl is bonded to at least one nitrogen. Now, the way that you actually make amides is that you take a carboxylic acid and an amine, and what happens is a dehydration reaction. So here, for example, ammonia with propanoic acid, we get rid of the OH group here off of the carboxylic acid, and we form a bond directly from the carbonyl carbon to the nitrogen in the amine. So here, what was propanoic acid, as an amide becomes propanamide. Here, propanoic acid can react with methylamine in the same way. Again, you lose a hydrogen from the amine and then the OH group from the carboxylic acid, and that gives you this compound here. So it's propanamide again, but this time we have a methyl group off of the nitrogen, so we call it N-methyl propanamide. We'll talk more about that in a second. Now, note this only works with ammonia, primary amines or secondary amines. Tertiary amines can't do this reaction because they don't have a hydrogen to give up. Okay, so let's go ahead and give me the product of the following amidation reaction. So given benzoic acid and methylamine here, tell me what amide is going to form from this amidation. Pause the video, work it out on your paper, and we'll take a look at the answer when we come back. So pause. Okay, let's take a look here. So what happens is we lose the OH group here and one of the hydrogens from the nitrogen. And this nitrogen then is going to form a bond to the carbon in the carbonyl. So now we've got an NC bond here. What was NH2 is now NH, and then a methyl group off of that. This would be called N-methyl benzamine. Okay, so let's go ahead and focus on how to name amides. So, and we're going to focus on basically the IUPAC names here. Don't worry about the common names. I'll mention any that need to be known as common names here. And what you do is basically you start from your carboxylic acid name, drop the oic acid, and add the suffix amide. So what was pentanoic acid becomes pentamamide. Now, any alkyl groups that are attached to the nitrogen can be named with the prefix N, okay? So in this case, we have two methyl groups off of the nitrogen on a 1, 2, 3, 4 carbon chain. So the 4 carbon chain tells us that it's butanamide, okay? And then the fact that we have two methyl groups here, we need to say that, well, they're on the nitrogen, so we're going to call it N dimethyl butanamide. Okay, let's go ahead and do this one together. So here, what we want to do is note, okay, we've got our amide here, that's this here, and how many carbons are in the amide chain? Well, there's 1 from the carbonyl, then 2, 3, 4. 4 total, that would be butane, minus the E plus amide becomes butanamide. Are there any substituents? Well, it turns out there's 1 methyl group right over here, right? And this methyl group is attached to the nitrogen. So to name it, we have to give it a location. It's N-methyl on top of butanamide becomes N-methyl butanamide. So go ahead. Okay, so let's go ahead and take a look. We're now ready for our first sample exercise. Just give me the IUPAC name for these. You don't need to worry about the common name for both the A and B. Pause the video here, give it a shot, and when you come back, we'll take a look at the answer. So pause. Okay, let's take a look here. So up top, you have 2 carbon amide. So that's ethane, right? Becomes ethanamide, like there. Also known as acetamide. That does come up every so often, but don't worry about that. And then down here, we have 1, 2, 3 carbons in our chain. So that's propanamide. And then an ethyl group on the nitrogen. That's N-ethyl propanamide. Okay, now amides really are important because not only are they relatively commonly formed, they're responsible for the linkages in our proteins. So amino acids link up in amide bonds to make proteins. And then there's also other compounds that are important for it. So for example, urea. Now you probably have heard of urea because it's the main component of urine. Okay, so urea looks like this. It's a carbonyl, and then it's basically an amide on both sides. So yeah, so urea is, again, usually removed from your blood by the kidneys, And this happens when proteins metabolize. So if you break down a protein, you end up with urea. And of course, it comes out in the urine, hence the name. Now, if kidneys malfunction, urea will not be removed from your blood, and it can actually build up to a toxic level in your blood. This is what's known as uremia. Okay, other examples are drugs. Going back to drugs, we have barbiturates here. Barbiturates are cyclical amides of barbituric acid. So phenobarbital, for example, or pentobarbital. So this is luminol and nambutol. They can be sedatives or sleep inducers if they're in large doses. And these are habit forming. So if you read like old books, like if you ever read like Hunter S. Thompson books, for example, he's talking about all sorts of different types of drugs. Like he mentions barbiturates like phenobarbital, which was in pretty common usage in the 1970s. Aspirin substitutes as well often contain amides. So like, for example, phenacetin or acetaminophen. So that's Tylenol, and phenacetin is, I think it's Excedrin. I could be wrong on that. I might be forgetting the actual name for the brand name for that. But both of these are used for basically like fever and pain relief, but they don't have an anti-inflammatory effect. So yeah, just kind of pointing that out. Okay, so let's talk about amide hydrolysis. Now, in the previous lecture, we talked about how esters can be split up in two different ways. We have acid hydrolysis and base hydrolysis. The same thing is true with amides. Amides can undergo acid hydrolysis when you react it with an acid in heat. And what happens is you form the carboxylic acid from the amide and the ammonium salt of whatever amine you have. So for example, here, ethanamide, you split it in half. What was this amide linkage between the carbon and the nitrogen? Now you're going to be left with a carboxylic acid, in this case, ethanoic acid, and you're going to be left with the ammonium salt of the amine. In this case, it's NH4, ammonium chloride. Note here that we're using the water is a reactant as well as the hydrochloric acid because it's actually consumed by the product. Now, base hydrolysis can also occur. And the difference here is that in base hydrolysis, what happens is you form the carboxylate salt rather than the carboxylic acid. And the amine that forms is the neutral amine, not the protonated amine. So here, for example, this is N-methyl propanamide reacting with sodium hydroxide in the presence of heat. The propanamide splits off and forms the propanoate with the sodium ion from the sodium hydroxide. The amine that's formed is just left over from this N-methylamine here. So that becomes methanamine or methylamine. Okay, let's go ahead and give it a shot. Why don't we try to draw the condensed structural formulas for the products from the hydrolysis of N-methylpentanamide with NaOH. So here, let's actually start. I'll do this on the annotation here real quick. So N-methylpentanamide, how do we draw that compound? Well, we know it's a 5-carbon chain with an amide. So that becomes 1, 2, 3, 4, 5. And it's an amide at the end. So this is going to be a carbonyl bonded to oxygen. And then it's an amide. So we know that the nitrogen is next. Okay. Now we also know that the N-methyl means that there's a methyl group on this nitrogen. So we can draw a methyl group here. And to balance it out, we know nitrogen is going to have 3 bonds. So we're going to have 1 more hydrogen bonded to this nitrogen. Okay, next step. We're undergoing base hydrolysis. So when we use NaOH, that means it's base hydrolysis. What that's going to do is it's going to split our molecule in half. We're going to have the amine that forms from here. Let's go ahead and do that because that's actually the first and easiest thing to do. So the amine that forms is just going to be this nitrogen. We know it's got a methyl group on it. And right now it has 1 hydrogen. But when it splits off, it's going to pick up another hydrogen from the NaOH and form NH2. In other words, it's going to be the neutral amine. Now, the trickier part is going to be what happens to the carboxylic acid. What was the carboxylic acid now is going to form the carboxylate. So we take our pentanoate Okay. We broke that carbon oxygen or carbon nitrogen bond, and now we formed a new carbon oxygen bond. And this oxygen is negatively charged. In other words, it's already been deprotonated. Now to balance that charge, we have a sodium ion from the sodium hydroxide to form our salt. So if we're naming it then, let's go ahead and name it. Over here, we just have a methyl group on an amine, so that's methylamine. And then down here, our cation is sodium, and then our anion is pentanoic acid as a carboxylate. That's pentanoate. So sodium, pentanoate, and methylamine. Okay. Okay, and if you want to see it in condensed structural form, that's what this looks like here. So again, this is N-methyl pentamide. We split that carbon nitrogen bond. That leaves us with the neutral amine in this case for the base hydrolysis and the carboxylate salt of the carboxylic acid. Okay, so go ahead and give me the condensed structural formulas and the line angle structures. Go ahead and do that too for A and B here. We have pentanamide and we have N-ethyl benzamide. So give it a shot, and when you take a look, when you come back, we'll take a look at the answer. So pause the video here, and we'll have the answers when you come back. Okay, let's take a look. So pentanamide is easy enough. It's 5 carbons on an amide, which means you have a carbonyl and carbon 1 onto an NH2. And I realize I maybe didn't tell you what benzamide was, but benzamide is just like benzoic acid, where you have benzoic acid here with his benzene ring with a carboxylic acid on it. Benzamide is just a benzene ring with an amide on it, like this. With an N-ethyl substituent, that means that we have an ethyl group coming off of the nitrogen on the benzamide. Okay, all right, well, that does it for this chapter. So go ahead, finish the homework now for chapter 14. You're ready to go. And yeah, let me know in the comments if you have any questions. Until then, I will see you soon. Bye-bye.